Students, in last class we discussed about the construction and operation of N-channel enhancement MOSFET. In that, we discussed the drain characteristics and transfer characteristics of N-channel enhancement MOSFET. Along with discuss the different region of operations of enhancement MOSFET, and we studied the circuit symbols of MOSFETs, enhancement MOSFETs. Today we discuss about the drain current equation and channel modulation of the N-channel enhancement MOSFET. So firstly we will discuss about the current equation in the MOSFET. So let us consider the N-channel enhancement MOSFET. In that we consider the cross section of N-channel MOSFET. In that the length of the gate or length of the channel is L. So the length of the channel is always equal to the length of the gate material, and width of the channel is W. It is also almost equal to the width of the gate material. So the channel and gate material is separated with the insulation material or dielectric material. Here we are using the silicon dioxide layer, so its thickness is nothing but Tox, and the capacitance between the gate and channel is oxide capacitance. So we are applying the positive potential at the gate, inversion layer will form. In the inversion layer we are having the negative charge. So gate material having the positive charge, inversion layer having the negative charge. In between we are having the dielectric material as silicon dioxide. So it is behave as a capacitor. This capacitance is oxide capacitance. This oxide capacitance is epsilon A by D. So epsilon is the permittivity of the silicon dioxide. So we can write epsilon oxide layer into A, area of the gate or channel, and D is the difference between the two places. The two are gate and channel are separated by the oxide layer thickness. So it is nothing but Tox. So from this we can write oxide capacitance is epsilon ox A by Tox. So here we are defining the oxide capacitance per unit area. So Cox equals to epsilon ox by Tox. Clear? And to create the channel in the enhancement MOSFET, we must apply the VDS value is always greater than the threshold value of the device. For a MOSFET, the net gate voltage we can write it is equals to VGS minus VT value. The net gate voltage or overdrive voltage. Yes. So channel voltage is VDS at drain end and 0 at source end. So we know that increasing the more drain voltage, what happens? The channel voltage is varying from 0 to VDS. So VDS is present at the drain end and 0 potential present at the source end. It is similar to the our JFET. So channel voltage decreases almost linearly from VDS to 0 along the length of the channel, and gate channel is separated by silicon dioxide. Gate channel is separated by silicon dioxide will form a parallel plate capacitor. Yes. So the amount of charge due to the electron accumulation in the inversion layer can be calculated. So we are considering it as a Q dash. Yes, Q dash equals to Cox into voltage across the capacitor. We know capacitor C equals to Q by V. From that we can write Q equals to C into V. So here Q dash equals to Cox into voltage drop across the capacitor. So we are applying the potential at gate equals to net gate voltage equals to Vs minus Vt, and channel voltage we are considering it a V at some particular point. So from that we can write Q dash equals to Cox into Vs minus Vt minus V. So Q dash is the charge per unit area. If I want to calculate the total charge in the inversion layer, then I am considering it as a Q. So we can write Q equals to Q dash into area of channel. So area of channel equals to L into W. So Q equals to Cox into Vgs minus Vt minus V L into W. So we know the current can be defined as charge per unit time. So drain current is flow of inversion charge per unit time. So IDS equals to Q by T. So Q equals to, we already know, C ox into Vs minus Vt minus V L into W by T. So L is the channel length and T is the time. So length by time equals to, we can write velocity of the electrons, velocity of charge carriers. So here we are considering the n channel. So velocity of the electrons. So we can write IDS equals to C ox into W into Vgs minus Vt minus V into small v. It indicates the velocity of the electrons. So we already know velocity is also written as mobility of the electrons into E. So we can write IDS equals to C ox into W Vgs minus Vt minus V mu n into E. So E is the electric field equals to voltage by distance. So the channel voltage is varying from the VDS to 0 along the length of the channel. So we are considering is a differential voltage dV and the differential length is dx. Yes, so we can write electric field equals to dV by dx. So to get the total current along the channel length, so we need to integrate along the length of the channel. So the length of the channel is L. So we are integrating the limits from 0 to L. And voltage also, channel voltage is also varying from the VDS to 0 from drain to source. So it is also integrated from 0 to VDS integration. So by integrating this equation, we can write x equals to 0 to limit L IDS dx equals to integration of 0 to VDS mu and C of W VGS minus VT minus V dV. So here integration with the limits of 0 to L will get, here it is IDS into L equals to mu and C of W VGS minus VT. Integration will get, it is equals to V, and integration of V equals to V square by 2. Now limits are 0 to VDS. By applying these limits, we can get IDS equals to mu n Cx W by L VDS minus VT into VDS minus V square ds by 2. This equation is applicable for both triode region and saturation region. Yes. If we consider the MOSFET is in triode region, then VDS value is very small, we know. So we can neglect V square, VDS square by 2 can be neglected. So it is, IDS is almost equals to the mu and C of W by L VDS minus VT into VDS. If VDS is constant, then drain current increases linearly with VDS. Here, so in this equation, if VDS is constant, then drain current is linearly with VDS value. We can write the drain to source resistance RDS, otherwise we can say it is a channel resistance, it is equals to VDS by IDS. So we can write 1 by mu and Cx into W by L VGS minus VT. This is the channel resistance or drain to source resistance. So this RDS value is a channel resistance. RDS can be varied by changing the voltage VGS. Yes, thus MOSFET can be voltage register in the triode region if VDS is smaller value. So when you are increasing the VGS value, then what happens? RDS will be decreases. Clear? So in case 2, if MOSFET is in the if MOSFET is in the saturation region, the drain current remains constant, we know. Yes, this saturated drain current can be calculated by substituting the VDS equals to VGS minus VT in standard equation. By substituting this VDS value in the standard equation, then we can get IDS equals to V n C of W by L VGS minus VT whole square minus VGS minus VT whole square by 2. So by simplifying here, we can get IDS equals to V n C of by 2 W by L VGS minus VT whole square. So drain current, this is a drain current if MOSFET is in saturation region. If the same drain current equation for the P channel MOSFET, we can write ISD equals to mu P C of W by L VGS minus VT VSG minus VT whole square minus VSG minus VT whole square by 2 in saturation region. Then we can write ISD equals to, sorry, here it is, mu p. Here I mentioned mu n, just consider it as a mu p. So ISD equals to mu p C ox W by L VSG minus VT whole square the triode region. Hence, of the MOSFET, we already know the transconductance is nothing but rate of change of drain current with respect to the gate to source voltage. Yes. So GM equals to dou IDS by dou VGS. This is, I am considering it is a equation number 1. In triode region, we know IDS equals to mu n C ox W by L VGS minus VT into VDS by VDS minus VDS square by 2. So from this we can write GM equals to dou IDS by dou VGS. So derivating with respect to VGS, then we can write mu n C ox W by L VDS. This is the transconductance in the triode region. Same in saturation region, we know IDS equals to mu n Cx by 2 W by L VGS minus VT whole square. So here we are writing the transconductance parameter Kn. Kn equals to mu n Cx W by L. This is also transconductance parameter or device parameter, and sometimes Kn mu x is also called as process transconductance parameter or process parameter. Yes. So we can write IDS equals to Kn into VGS minus VT whole square also. So by derivating with respect to the VGS, we can write VGS GM value, then mu n Cx W by L VGS minus VT. Yes. So we can write Kn into VGS minus VT also, and GM is also written as Kn into under root of 2 IDS by Kn. Otherwise we can write under root of 2 IDS into Kn. Clear? Modulation. So when the channel length modulation occurs in the MOSFET when it is operating in the saturation region. Yes. So we know when I are increasing the more VDS value than the overriding voltage, then what happens? When VDS is greater than VGS minus VT, then pinch off occurs at the delta L distance from the drain. Due to this, effective channel length decreases by delta L distance. This decrease in the channel length due to the increasing VDS in saturation region is called channel length modulation. So anyway, the modulation is nothing but one parameter varying with respect to the some other parameter. So in previous we discussed the base length, base width modulation. Base width modulation is nothing but the effective base width is varying with respect to the connected to base voltage. Here the effective length of the channel is varying with respect to the VDS. So the decrease in the channel length due to the increasing VDS in saturation region is known as channel length modulation. Due to decrease in channel length, what happens? Channel resistance decreases and drain current also increases. That means drain current does not remain exactly constant in saturation region. Yes. So we can write now it is L dash. Why? Because it is reduced by delta L distance from the drain. So initially it is L distance. Now it is effective length becomes L dash equals to L minus delta L. So we can write IDS equals to mu n Cx W by L and mu n Cx W by 2 L dash. Why? Because we are writing in the saturation region. We just made it whole square. So L dash can be written as L minus delta L. So now it is mu n Cx by 2 W by L minus delta L into Vgs minus Vt whole square. Clear? So this equation indicates the again saturation current equation. So we can write IDS equals to ID sat into 1 minus delta L by L whole power minus 1. So we know 1 by 1 minus x is nothing but 1 minus x power minus 1. We can write it is equals to 1 plus x if x is less than or equals to 1. Here also delta L by L is very small compared to the 1. So this delta L by L is less than or equal to 1. So we can write it is equals to IDS equals to ID sat into 1 plus delta L by L. So here delta L is directly proportional to the change in the VDS value. We are increasing the more VDS, then what happens? The delta value is also changes, the length also changes. So the delta L is directly proportional to the change in the VDS value. So now removing the proportionality, we are keeping the proportionality constant. It is a lambda dash. So I am considering the lambda dash. So now it is delta L equals to lambda dash into delta VDS. So I am dividing with the L in both sides. We can write delta L by L equals to lambda dash by L into delta VDS. Yes. So lambda dash is a constant and L is dividing on both sides, it is also constant. So by replacing lambda dash by L with the again constant delta, sorry, again constant with lambda. So delta L by L equals to lambda into delta VDS. This is equation number 2. Substitute this equation number 2 in the equation number 1. IDS equals to ID sat into 1 plus lambda delta VDS. Here lambda is the channel length modulation and units of lambda is per volt or volt inverse. Yes, if channel length modulation does not occur, then lambda equals to 0. Lambda is nothing but it's a measure of how strong channel length modulation occurs. Clear? So channel length modulation occurs when we are applying the more VDS. Otherwise we can say when it is in the saturation region. Otherwise we can say VDS is greater than VGS minus VT. So in this channel modulation, the length of the channel is decreases by increasing the VDS in the saturation region. Clear? This is the channel length modulation.